So what I'll do is, well, first, give a little overview. Hold on, I'm trying to get rid of stuff on the screen. Uh, okay, great. So, bigger picture of neurosymbolic methods. I think a useful kind of framework is the one that Henry Kotz put out. If you saw his really nice KRHCAI lecture, where he has 6 different categories. So I won't go into them, but his talk is worth checking out if you're interested in this kind of thing. What are some of the most common goals? They're pretty similar across most neurosymbolic approaches. I would say a big one is understandability. Now, if you look at these patterns of different approaches, they generally maintain 2 representations if you really look hard at them. So they're kind of neuro plus symbolic, meaning 2 glued together in a sense, and often, or almost always, they're actually, you need them both at the same time, meaning you have the same kind of information represented at the same time. So that, argue, is a bit counter to understandability, because one of them generally is symbolic, that's sort of understandable, but the other one isn't. If you're going to debug it, you need to actually get into the other one, the black box one. Compositionality, I think I don't have to convince folks here. Several folks have argued for it, and I think probably all have that, or at least some sense of that, it's useful. It's maybe even essential. And one upshot of that could be task generalizability, because of the reusability you would get from the modularity. And of course, in general, being able to handle complex problems. I would say it's even deeper than that. The upshot of being able to do reasoning, it's actually generality as well, because it's arguably the only way to get to entirely new situations you haven't seen something close to, is you've got to go back to first principles, so to speak, chain together those principles for a very new situation. Okay, but a weakness, some of these things are generally not met in most neurosymbolic approaches, would argue. Generally not compositional, or at least somewhat compositional, but not fully. Reasoning often is not, you can sort of argue there's some kind of reasoning-like capability, or learns to reason or something, but going all the way to rigorous reasoning is rare, let's just say, in these methods. Rigorous meaning, say, sound and complete. So, so I'll just give you a little summary, just in case you fall asleep later. On the next 3 or 4 slides, I'll just summarize the work, and then I'll super quickly go through the details, if you will, and then anyone who has questions wants to go back in the QA period, please do so. So we introduce a new approach, logical neural networks, or LNNs. And the idea is that, or what's kind of different maybe, is that we're doing this neurosymbolic integration at the neuron level. So on the left here is supposed to be a picture of the standard neuron. I put a question mark in the middle, meaning the interpretation or semantics of that neuron are not obvious. So it can represent a lot of things, or it's not clear what it represents. So on the right is sort of our new neuron, which the left neuron is a special case of. And we add a few things. Really, the most essential thing we add, which is maybe counterintuitive, is the ability to go backward. Instead of going upward from the x's to the y's, we add a way to go from the y to any of the x's. And you can't actually do that, in general, exactly, always. So you end up having to have bounds. Okay, but I'll come to that later. But an upshot of these modifications is that you can actually show that you do true logical reasoning. Now, the reasoning is more general than classical reasoning. And one way it's more general is that in classical reasoning or logic, of course, truth values are either 0 or 1. Here, we can say we do real valued logic, where truth values can be between 0 and 1. And we'll map all this to common ways that people have formulated real valued logics. Okay, so, and it's important that to us that the standard neuron is a special case of this funny new or modified neuron, because it means that you can now have a single network in which some of the neurons can have semantics, and some of the neurons are just subsymbolic, like your standard neurons. Or your standard picture maybe is having subsymbolic lower level networks that are close to perception, say, and then higher level semantics, sort of above, sort of how many people think about how you would combine these two kinds of things. Okay, I think it's important, or if you're a reasoning person, comparing this to classical logic and reasoning, what's different here is that we can handle inconsistencies and incompleteness, or in other words, realistic knowledge bases where not all of your statements are necessarily true. They can conflict with each other. And so we have actually a way to handle contradictions and via these partial truths and weights. Okay, so that's logical neural networks. Part two of this is a way to, so far, I've just described a way to represent, you could say, logical statements with weights and with an interpretation of logic. But in other words, given a fixed structure or set of logic statements, it showed that it's actually also a neural net. Here, or part two, is a mechanism for learning new logical rules or adding structure. You could say extending the discrete structure. Okay, so this is rule induction or inductive logic programming. And under submission, we have a state-of-the-art way using logical neural networks to do that. Okay, and then what we're primarily using as a showcase and testing ground for this is language understanding. And this is the idea in general of translating the natural language text into logic, and then do reasoning on the logic, and then answer the question. Potentially also then go from the logic representation back out to text. That we haven't done yet. But that's our next wave. Next year we'll be doing that. Now, and here's a little example, but we can go into this later. This could say actually works in terms of getting state-of-the-art results in multiple tasks. At least 4 of them are knowledge-based question answering, entity linking, rule induction, and reinforcement learning, even where the policy is represented by logical rules. All this interpretable or reinforcement learning. Okay, so that's the quick summary. Now you could say what this is none of these 6 doesn't correspond to any of these 6 sort of usual patterns of doing neurosymbolic integration. It's not exactly gluing 2 things together. It's more, you could say, pointing out that actually neural nets with a slight modification are a symbolic system, which maybe is odd and surprising. So I call this neuro equal symbolic. Okay, so, and then I'll go into that a bit more. Now, what are the upshots? There's a single representation now, not 2. It's entirely human readable, of course, except for the subsymbolic neurons, but you know, how they work together is a lot more seamless, arguably. The you know, if and when you have an interpretation of semantics to a neuron, of course, it's it really is readable as logic statements. So a neural network, it's funny, new kind of neural network, is actually completely compositional because logic is completely compositional. And you can show soundness and completeness. Okay, so really quick story. We go back to the beginning. McCulloch, the very first neuron proposal, McCulloch and Pitts, 1943. So probably no one remembers this exactly from experience, but it turns out that the idea was that for a neuron, that it is exactly a logic gate. And this idea, this, you know, this is the actual point of the paper. This connection between neurons and logic gates sort of hung around a little bit, but kind of dissipated and was lost, arguably, except for, you know, a few tiny threads, and emphasis, you know, moved on to other aspects. But at least here at this stage, well, here there were no weights and there was no learning. It was there's simply a threshold parameter that if you change it, gives you different kinds of logic gates. Then key step, weights were added and learning. There's still a logical connection, which is that in and behavior, say, within a certain region of the weight space. And here's an example. So you still have a logical connection. So sometimes, another way to say it is sometimes a neuron can act like a certain logic gate, depending where the weights fall. Okay, but it's starting to sort of loosen up, and can be an AND neuron, can be some other kind of neuron, depending how things change during learning. Another big step, of course, was realizing we need multiple layers, and this eventually leads to many, many layers, deep learning, and so on. Part, and then, you know, that how do you handle that or allow that? You make the activation function differentiable. Now, arguably now the most common, or at least as common as sigmoids, is the ReLUs as the activation function. Now, of course, the output here is not is no longer just 0 or 1. So before in the perceptron, this activation function is this step function, 0 or 1. But here, no longer, right? So now, of course, if you learned classical logic, and this is not, there is no connection anymore to classical logic. So because truth values are 0 or 1. Now, one little thing we can do is go, oh, okay, well, but near the ends, and shown in red here, near the endpoints at least, it's almost 0 or almost 1. If we want, we could actually add some constraints to try to make us go to either region. So that's one modification we could start to make to try to force it to act a little bit more like a classical logic system, which we can interpret. Okay, and then here's an elaboration where you add slacks. If you're an optimization person, you like to do this kind of thing. It gives you also a way to control the degree of adherence to logical behavior. Okay, but the real, then, a bigger realization is, oh, but there are real valued logics. In fact, they're pretty old. They go back almost as old as, classical logic. So I'll call them real valued logics. Have come under different names: multi-valued logics, fuzzy logics, and these are different ways to essentially make an analog to and or and applies, and potentially other gates, where you have you have an output that's 0 or 1. All of them have or between 0 and 1. All of them have classical logic as a special case, the endpoints. Here are at least 3 common ones. Okay, and Zade's logic is actually close to this Gödel logic. Okay, but somewhat fortuitously, one of them, actually maybe the most worked out, arguably, Lukasiewicz logic, is actually, it corresponds exactly to the ReLU function. If you plot, these logic gates. Okay, so now you're hopefully starting to see the connection, but this is more general than just Lukasiewicz logic. So it actually can do this for any of the real valued logics. And one key step we're going to do, which is not that hard, is to generalize the logic to add weights on the terms. Okay, so here's an example: weighted Lukasiewicz logic. We defined your and or and so on in a weighted fashion. Okay, now that's just the logic. You need a second part to have a logical system. You need inference rules. So in fact, you really only need one to be able to show soundness and completeness. You need modus ponens. So so here are different classical inference rules. Okay, but and once you have some kind of inference rules, you can show potentially soundness and completeness. Definitely show it in classical first order logic. but this hadn't been fully established for real valued logics, which is maybe surprising. So at least, not in general. Okay, so in some work we did, we showed a very general scheme that holds for all of the common real valued logics that sound and what we might call strongly complete. Okay, now this is all great, but we'd like to, and this paper is kind of, a little bit abstract. But we'd like to map this to neural net infrastructure, which is maybe a funny thing, but I'm going to show that we can do soundness and completeness, or sound and complete inference by message passing in a neural net like thing. Okay, so now here's the key. So think about, or pretend this is for a second, it's clear if this is an implies neuron. So then to do modus ponens, which is, if you know that A implies B and you know A, then you know B is true. So there, A, when you write this as a neuron, A and B are the inputs, the X inputs, and A implies B is the Y. So to implement modus ponens, we can see you're really going backward. You're saying if you know A implies B, or the Y, then, and you know one of the inputs X, you know the other input B. Okay, so that's the equivalent of going backward or downward through this neuron. Okay, so that gives us, work that out a little bit, and come up with a scheme we'll call the upward-downward algorithm that we can show does logical inference. Okay. And then you end up with bounds because of the non-uniqueness of X's given Y's. Okay, but that's may seem like a problem, but it's actually turned out to be a bonus because it allows us to specify imprecision in knowledge or ignorance. You could think of it as a generalization of missing values. Okay, I'll just flash this. Now we put all this together to make a system. What are the inputs and outputs? Well, the inputs are logic statements so far. You get from somewhere, let's say a knowledge base or knowledge graph or other policies or whatever. So natively relational. And your training examples are like instances of or examples, just as in learning, regular learning, except now any subset of the variables can be both input and output. So I call this, it's probably an existing name, but I call this any task learning. So you can, because of this ability to go in any direction in terms of flow through the network, anything can be an output and anything can be an input. And you can ask about any variable. Okay, the interesting, so how do we set up learning? We have the usual kind of loss, but we'll add this extra term we'll call contradiction loss. And this basically is looking at all the variables together, and to see when to penalize you if when and if you have variables saying different things. Okay, so the upshot there is we allow contradiction, which can happen, of course, when you're fusing together large knowledge bases and so on. It's okay, we just minimize it. And here's the punchline, is that we have this small modification, which is really downward inference, and the constraints, which you don't actually need. So that's why I say it's a minor change. Then you have your standard neural net equals a set of logic statements, and inference or propagation in a neural net equals logical inference. It's just that the logic is a weighted real valued logic. Okay, several things are special cases. Standard neural net is a special case. Even with modern activation functions, like ReLUs, and classical first order logic is a special case. Now, one limitation here is that, which is like almost all neurosymbolic methods, we're really talking about grounded first order logic. So in something I'm not showing here yet, something we're just putting out now, about to submit, we have a lifted version, which hopefully if you're interested soon, we'll be able to talk about. But so far here, when I say first order logic, I mean grounded finite domain first order logic, like almost everything else, Markov logic networks and so on. Okay, now super quick, some details. So here's the knowledge-based question answering. Here's an example where you actually need reasoning. Though it seems like an innocent example, was Roger Federer born in the United States? What you really have from wiki data is some different facts. You have Roger Federer was born in Basel. Somewhere else you have that Basel is part of Switzerland. Somewhere else you have that Switzerland is a country, and somewhere else you have the USA as a country. So you have to, of course, put these together, and you need an extra piece of knowledge that says you can only be born in one country. And then you can conclude the answer is no. Okay, but so one subtext of this is reasoning, even for simple things, many simple things can be essential. Now, of course, your sort of standard approach to QA using neural networks generally selects from pre-canned existing sentences. So, and typically the results are on one-ish data set. So we show achieve the state of the art on multiple QA data sets. This table up here of results a little old now, but this is a quick picture of how this works. There's this first step of semantic parsing to get it to logic. That is sort of, or the really hard part, you could say. And in there, you have to do entity relation linking to link to the right concepts. And so, one nice thing is that we're able to show that all of these pieces are state of the art in their own sort of comparison space. Here's some of the papers if you want to find out more. We like this set of results also because this is a space where we're competing with non-neurosymbolic methods. So It's not just that we're beating other neurosymbolic methods, but this is a case of neurosymbolic actually beating, regular. So in a highly competed kind of space. I'm not sure if this is the first such result, but I'm sure people will tell me there are other results like that, but at least it seems to us a significant one. So, and I think, hopefully we'll be seeing more of that in general, neurosymbolic beating standard deep learning in various ways on different tasks. So here's a little bit about the rule induction. This is, of course, a search process. You do have to supply a sort of template kind of for the rules, or at least how long are the rules in the general form. And so, you're not going to search for rules that have 5 conjuncts, or you have to specify that, the bounds of it. And we do use embeddings in concert. So that's one way, at least, that we can take advantage of things like large language models in principle. Here's a little bit about the optimization. We this is a sort of fancy approach to the optimization. We have several approaches, but this is a primal dual ADMM style optimization scheme, which can be made actually distributed. And you see some pretty good performance here. Now, one big direction we're taking is to do reinforcement learning, where the policy is actually interpretable because it's logical rules. And further, the larger kind of goal here is to be able to do reinforcement learning, which is sort of really, really inefficient in a way, requiring a huge number of trials generally, using knowledge to hopefully dramatically reduce the number of trials that you need. So we're starting to see results like that, something like a 10x reduction in certain problems. So here's some of our papers starting to look at that. And then the last thing I'll mention is, which is not quite integrated yet, but an approach to doing theorem proving using embeddings to guide do proof guidance or axiom selection. And this is almost now beating all of the sort of hand-tuned reasoners. So this is what we have in mind to actually guide ultimately LNN proofs. Okay, really quick, how does this compare to sort of other major approaches? So here's a certain problem or setup called smokers and friends. Markov logic networks are maybe the best known neurosymbolic type approach. That and problog and sort of variations of problog are based on Markov random fields. I would argue this is an example of maintaining 2 representations. So you have the logic statements, which is sort of what you really want to represent and interpret. But then you could say I have a compiler that compiles that to a Markov random field, which loses the directionality. It becomes a clique. Your logic statements become cliques with some numbers on them, which are not exactly probabilities. So, and you have you turn this into a satisfiability problem, and you do something like MCMC. So you end up with something computationally difficult. And the interpretation, you can of course interpret the logic, but that's not your actual model. Your model is this Markov random field. So, and then you have embedding a whole bunch of them. One of them is logic tensor networks, which is actually, in a way, a big idea. It's saying that your concepts are now vectors. So I think there is something, there's a lot to be worked out there that could be very interesting. But so far, at least, the reasoning of that is sort of the weak point, arguably. It's hard to say how rigorous that reasoning is to date, but I think a lot more will be worked out in those approaches. Now, in our approach, it is logic, so it's compositional and directly readable. And of course, until you start to add in subsymbolic neurons, but at least you have a sort of a clear role for those symbolic parts. Okay, this is a first take on how to put a layer on top that makes it explainable. There's a lot more work we need to do here to actually take humans through the reasoning process. And, hopefully, or at least what we're aiming for ultimately is a kind of enabling a philosophical shift where humans, because humans are needed kind of to make knowledge, or at least interpret knowledge and fix knowledge and so on, they become actually an integral part as opposed to a bystander in the construction of AI models. So I'll just mention sort of where we're going next. Interactive fiction is something we've started to work on. We think it's a nice, difficult domain for general AI that is actually harder to game than other things, other tasks. And we're interested in also, I think like others, trying to fix or counter some of the issues of large language models. Try to prevent nonsense generation and some of the other issues. And these are some of the many fundamental threads we continue to work on. Here's some of the papers and representation of our many collaborators. That's it. If you want to find out more, please reach out. We're always looking for like-minded collaborators. So thank you.